Okay, so in this video, we will be proving this nice identity in two different ways. The first of which is correct, so to speak, and the second is kind of overkill. So first, let's prove it in the correct way. So we can rewrite this product on the left by using the exponential version of the sine as follows. So it's e to the pi I k over n minus e to the minus pi I k over n over 2I. And you can multiply the numerator and the denominator by e to the pi I k over n, and so this thing inside becomes e to the 2 pi I k over n minus 1 divided by 2I e to the pi I k over n. And now the product of all these factors is equal to, so the product of the numerators, which is as follows, and the product of the denominators is equal to, so 2 to the n minus 1 times I to the n minus 1 n times e to the pi I over n times 1 plus 2 plus all the way to n minus 1. And now look at this factor over here. So let me erase the board. So this factor at the bottom here is equal to e to the pi I over 2 times n minus 1. And the reason is that this is the n minus 1th triangular number, and so it's equal to n times n minus 1 over 2. And when you multiply these two, you get this. So sorry, that's not an equal, of course. I mean, this is equal to that, and this is equal to e to the pi I over 2 to the n minus 1. But that's just equal to I. So that's equal to I to the n minus 1. So we can replace this factor here by I to the n minus 1. And we have two of these, so we can just write I to the 2n minus 2. And I to the 2n minus 2 is equal to I squared to the n minus 1. So that's I squared to the n minus 1, which is just minus 1 to the n minus 1. And therefore, we have the following product. And now we want to evaluate this numerator. And the way in which we will do this is by reminding ourselves of the nth complex roots of unity. So when you factorize this polynomial, whose roots are exactly the nth roots of unity, you find that this is equal to z minus 1 times the product from k equals 1 to n equals 1 of z minus e to the 2 pi I k over n. So these are the non-trivial nth roots of unity. And when you divide both sides by z minus 1, you find that is equal to this product over here. But if you take the limit as z goes to 1 on both sides, then this product becomes, so when you take the limit as z goes to 1, this product becomes equal to minus 1 to the n minus 1, because they are n minus 1 factors, times this product which we want here. So times n minus 1 e to the 2 pi I k over n minus 1. So, but that's for this product. What about this one? To evaluate the limit as z goes to 1 of this expression, we make use of L'Hopital's rules. And of course, we differentiate the numerator and the denominator, and then we put z equals 1, and we find that this limit is just equal to n. So now we come back to this. We can multiply the numerator and the denominator by minus 1 to the n minus 1. So that just cancels out because it becomes minus 1 to the 2n minus 2, which is even. And this thing over here, we've already shown that it's equal to n. And so we can just substitute n over here, and this is exactly what we wanted to show. So that was the correct way, so to speak, of proving this identity which we wanted to show. And now I'm going to, just for fun, prove it in an overkill way. So let me erase this. So for the overkill way, let me just write it. So we are going to make use of Gauss's multiplication theorem. So Gauss's multiplication theorem for the gamma function. So we recall what Gauss's multiplication theorem is. So that's the gamma function, which generalizes the factorial function to the entire complex plane, except with some poles. So Gauss's multiplication theorem says that if you take this product all the way to the term gamma of s plus n minus 1 over n, this product is equal to n to the half minus ns times 2 pi s minus 1 over 2 times gamma of ns, and here s is any complex number whatsoever. So Gauss's multiplication theorem is really a generalization of Legend's duplication theorem, and maybe later in some playlists we'll prove all these, but for now we are just going to use it. Alright, so since this is valid for all complex numbers, let's first put s equal 1 over n. And when you put 1 over n on this side, you find that gamma of 1 over n times gamma of 2 over n, all the way to gamma of n over n, which is really 1, is equal to n to the minus half times 2 pi times n minus 1 over 2. And but you could also put s equal to 1, and 1 is really n over n. So if s is equal to 1, which is n over n, you find that gamma of n over n times gamma of n plus 1 over n, all the way to gamma of 2n minus 1 over n, this is equal to n to the half minus n times 2 pi n minus 1 times gamma of n. But now we can multiply these two these two products together, and remember that gamma of 1 is just equal to 1, and you will find by multiplication that, so let me erase this. Gamma of 1 over n times gamma of 2 over n all the way to gamma of 2n minus 1 over n, and that's equal to 2 pi times n minus 1 times n minus that's 2 pi times n minus 1 times n to the minus n times gamma of n, and you can rewrite it like that. That's n minus 1 factorial because n is a positive integer over n to the n. And okay, so we've got that far. Let me erase this. Now we are going to make use of another formula for the gamma function called the Euler reflection formula. So the Euler reflection formula states that gamma of 1 plus s times gamma of 1 minus s is equal to s times pi over sine of pi s for any complex number s which is not an integer. And when we successively put s equals, so successively put s equals 1 over n, 2 over n, all the way to n minus 1 over n, in this formula for some positive integer n which is greater than 1, and then you multiply the result together, you will see that you get the product of the terms on the left are exactly this product here. So it's really straightforward, and I leave it as an exercise, a very easy exercise to you. But when you multiply the product on the right, you will find that you obtain, so the product on right, it's equal to n minus 1 factorial times pi to the n minus 1 over n to the n minus 1 times the product from k equals 1 to n minus 1 of sine of 2 pi k over n. But so this formula over here is equal to this formula over here. And when you equate these two, you get exactly what we wanted to show. So that this product is equal to n over 2 to the n minus 1. Right, so actually I've just noticed I've written a 2 here, which should not. So, okay. So now that we have proved the product which was required, let's just have a bit more fun before I end this video. So now if I ask you to sum this series, so 1 plus sine of pi over 2 plus sine of pi over 3 times sine 2 pi over 3 plus sine of pi over 4 times sine of 2 pi over 4 times sine of 3 pi over 4. And just so that you see the pattern, sine of pi over 5 times sine of 2 pi over 5 times sine 3 pi over 5 all the way to 4 pi over 5, and you continue on like that. So how would you evaluate this series? Well, now that using the product we've just shown, we know that this series, which is actually equal to this, and I've just rewritten it, this expression is equal to this series by what we've just shown. So n over 2 to the n minus 1. And this series is just 1 over 1 plus 2 over 2 plus 3 over 2 squared plus 4 over 2 cubed plus 5 over 2 to the 4, and so on. And this series is easy to solve by a trick that everybody knows, but we'll just do it for fun. So if we call this series S, then actually let me rewrite it here. So it's 1 over 1 plus 2 over 2 plus 3 over 2 squared plus 4 over 2 cubed plus 5 over 2 to the 4, and so on. Now, the obvious thing to do to evaluate this series is to multiply it by half. So half S is equal to 1 over 2 plus 2 over 2 squared plus 3 over 2 cubed plus 4 over 2 to the 4, and so on. And of course, we subtract these two series. So I'm subtracting these two. Get 1 plus 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the 4, and so on. And this series is just equal to 1 over 1 minus half, which is a geometric series, and that's equal to 2. And therefore, S is equal to 2 times 2, which is 4. So the previous series in the sines which we wanted to evaluate is equal to 4.